How does this $100 motor compare to the Clearpath? Let's find out. Welcome back to Cloud 42, I'm James. If you've been following the channel, then you know we've been testing NEMA 23 motors for the electronic Leadscrew project so that I can come up with something that I can feel good about recommending. We've done some testing of open loop steppers, closed loop steppers, and even the Clearpath servo. And today I've got one more servo that I would like to test. If you're interested in understanding the methodology, I'll put a card up here. You can go check out the previous video and see the other motors that I've tested. When I was looking for motors to test, I did look at Stepper Online because I have purchased some motors from them in the past. In fact, that's what I'm using on my CNC machine. And I looked through the closed loop steppers that they offer, and there was one that looked really intriguing to me. And it's this new YE series closed loop stepper. They claim 4 Newton meters. That's probably holding torque like all the others. But the thing that's fascinating about this is if you look in the manual, they have this claim that says low torque attenuation up to 3,000 RPM. Now, 3,000 RPM is just ridiculously fast for a stepper motor. And for a stepper motor with, let's see, what do we have? 2.6 millihenries inductance. There's no way. I mean, there can't be, right? So I thought it would be really interesting to test this and see what they're doing with this driver to get, quote, low torque attenuation up to 3,000 RPM. But I don't really want to spend my money for it. So I sent them email and offered them the opportunity to send one of these to me for free for testing. And this is the response I got. If you want to run the motor at 1,500 to 3,000 RPM, I highly recommend you use our integrated servo motor. Then they give some specs on the different motors. So for the 180 watt integrated servo, they're claiming 0.6 Newton meters between 1,500 and 3,000 RPM constant, and it can generate 3 times that for 10 seconds. So that actually sounds kind of interesting to me, especially if we run it at a deeper gear reduction ratio. So I said, yeah, I'm definitely interested, and they sent me one. So this is the motor. It's a 180 watt servo rated up to 3,000 RPM, 0.6 Newton meters, and this will run 20 to 50 volts DC. I think the manual suggests 36, but I spoke with them, and yeah, 48 volt DC is perfectly acceptable. You get higher performance at 48 volts with the expense of just a little bit more heating. So looking through all of this, this looks really interesting. It's just a NEMA 23 motor. It's got the integrated servo on the back. There are a couple things that are a little bit odd about it. It has, for one thing, it's got the pulse and direction input, but there's no enable input. I can live with that as long as it's not going to heat up when, like if I switch off the electronic lead screw, if this isn't just going to sit there generating a lot of heat or making noise, then that should be fine. It's kind of cool. It's got screw terminals to hold in the power connection. It's got your normal serial connection for connecting up the programmer. And then it's got a few dip switches to set a few things, but most of the interesting stuff you have to do via the serial port. So they sent me one of these, and we're going to test it. Okay, I've got the motor set up here on the test stand as usual, and before we do anything, let's just power it up and see how it behaves. Okay, that's on, it's holding steady. And the first thing I notice with this motor is that it's not really rigid. If I push it off center, it does return, it'll fight and come back, but it allows a lot of movement. Now compare this to the stepper motors, which don't really do this. If you press them hard enough, they'll eventually lose the torque battle, and you can cause it to lose steps, but they're very rigid in their position. And the Clearpath, once it's tuned, is exactly the same way. It's just solid. You can put as much force as you want on it, and it doesn't really move until eventually you overcome the torque capability of the motor, and then suddenly it just breaks. And this is very much not like that. This is very squishy, which, is probably okay for some applications. I'm a little bit concerned for the electronic lead screw, because this means that when we enter a cut and the load suddenly comes onto the motor, I'm concerned that it will get behind and then fight and catch up, but by then the thread that we're cutting will be damaged. I'm not sure how big a deal this is, but let's get the software connected to this and see if we can tune this and make that a little bit more rigid, a little bit stiffer. I think stiffness is what they call it. That's what it says on the side here. So to configure the driver in this, they provide a link to the software down here on the bottom of the page, and you can just download it. And spoiler alert, this link that's there now is the correct software for this driver, but the software that was there a couple of weeks ago when I started playing with this definitely was not. So I downloaded the software, and this is just a Leadshine driver inside, so it looks like any of the other Leadshine Pro Tuner software editions, but it would not connect. No matter what I did, I could not get it to connect to the serial port and actually talk to the driver. So I sent email to their tech support, and they responded immediately and said, seems like the software is wrong, and they gave me a new link. So I followed this link, downloaded that software, and guess what? That software didn't work either. So I know this thing has a Leadshine driver in it, and I figured, okay, well, Leadshine, it's a little bit odd that they don't combine the support for all of their drivers into one edition of the software. They have a different edition for every driver. But I went out to their website, and they've got a document telling you how to choose the right Pro Tuner. None of this stuff about the serial numbers match. Some of it kind of matched, but it didn't quite match up. And long story short, I just tried them all. I downloaded all of them. I tried them all, and not a single one would connect to the driver. So I wrote back to Stepper Online Tech Support, and they wanted photos of my connections, which, that's totally fair. They don't know if I'm just screwing it up. So I took photos of everything, sent it back to them, and they said, can you confirm whether you're running Windows 7 or Windows 10? Because the software is not compatible with Windows 10. Can you use Windows 7? Which is sort of an odd request, given how old Windows 7 is. So I responded and told them that it's end of life, hasn't had security updates for over a year. I don't have any computers running it, but maybe I could set up a virtual machine. And they say, yes, set up a virtual machine. We checked with Leadshine, and they told us most of industry systems are currently running Windows 7. I hope that's not true. But if that is true, it does explain why we see another company getting ransomware just about every day in the news. Anyway, I did set up a virtual machine with Windows 7, and guess what? It did not work either. So I wrote back, and they said that they checked Windows 10 on their side, and yes, it actually does work, so it might be a problem with my RS-232 to USB cable. So they went ahead and just sent me one of theirs. Now, I was using a Prolific PL2303 USB to RS-232 serial cable. It's the same cable that I use to configure my other drivers, but for some reason they're thinking that maybe it's the problem, and sure enough, it actually was. They sent me one of their drivers, which is just a different Prolific chip, and it worked great. Worked under Windows 10 with the new software, and it connected right up. So yeah, I don't know. That's a really odd one. However, when I actually got it up, this is what I was faced with. So these are the parameters. And there's just a little bit of information. There's a bunch of stuff like loop gain, control mode, auto gain tuning, machine stiffness. That's the one that we really want to configure. And there's another one here that's kind of key, which is the ratio of inertia. So I cracked open the manual to take a look at this. And the manual's got all kinds of information about connecting it. One of the things here is the parameter list. And so we can go in here and look, control mode setup, real-time gain tuning, scroll down and look at this. So this is the first one we want. Control mode setup, I definitely want position mode, not velocity. So the values are 20 and 21, position mode is 20. But if you go look at the software, control mode is set to 4, and it says the correct values are 0 to 10. I messed around with this a little bit and got the driver to do some weird things, but this is definitely not the same setting that's described here in the manual. So I figured, okay, let's just skip that. Let's go look at this machine stiffness. That's the important one. It's set to 11. The values are 0 to 31. The manual says the value should be 50 to 81, and the default is 70. Well, this value is actually printed on the outside of the motor, and it definitely says 11, and you can use dip switches to turn it down, but I actually need to turn it up. And I messed around with putting some of these numbers in, and it did not behave well at all. So I set it back to the defaults and wrote back to them and asked what was going on, and explained what I'm trying to do, and gave them an example of one of these and asked if I have the wrong manual. And their response is, sorry, the manual's not updated. Can you get the motor to run with the defaults? So I explained why I'm concerned about the soft positioning and that I need precise positioning for CNC, essentially, for threading. And the response is, it's too small a stiffness. Try boosting it to 13 or 14. So we can do that. I'm a little nervous not having the manual. And when you go into the manual, there's a section here at the end that talks about how to set up the ratio of inertia and how to do the auto tuning. And it steps you through running these loops where it runs the motor back and forth, and you can look at the response curves and adjust the parameters. But of course, none of this works. If you actually try to follow these directions, the driver panics because, it's the wrong manual. But given all of that, we do have directions from them to go ahead and try to boost this number to 13 or 14, so we might as well go give that a try. The other thing that does seem to work in here is the command pulse count per revolution. It's set up to take 4,000 counts per revolution, and I really want something more like 1,000 or 500, so we'll see if we can change that. That one seems fairly safe, and we'll see what happens. Okay, I've got what I think is the correct software, and this is actually the latest thing that they now have linked, which is different from all of the ones that I've tried before. And I've unpacked it, and let's give it a shot. Search, seek drive. And it found it, and I will connect. Okay, PC version 2.2 and driver software version 3.02. Okay, so let's go into the settings. And it takes a little bit to figure out. Unload means to transfer from the drive to the software. So I'll click unload to make sure we have the correct value. And it looks like this is by default set to command pulse counts per one revolution of 4,000. I'm going to change that to 500, and we'll talk a little later about exactly why I picked that value. And the stiffness should be PR 0.03, like he said. And the default, it is set to 11. Now he told me to try increasing this to 13 or 14. Let's try first increasing it to 12. Let's not get crazy. So there's 12, and I just heard the tone of the motor change. It's much more, it has a little bit of sound. Let me see if you can hear that. Just kind of, there's a little bit of background chatter, and you can kind of hear it there. That's definitely a little bit stiffer. Not quite as stiff as I would like, but it's better. Let's keep going. 13. And it just got louder still. That is much stiffer. It's reacting quicker. Let's try 14. Okay, so that hit resonant feedback. And what happened there is we've got the mass of this pulley on here, and so I think that's probably, that's not going to be there in the finished system. It'll be a much smaller pulley, so we might be able to go that high on the final installation, but for now I think 13 is probably as high as we dare go. In fact, yeah, let's go ahead and try it there, and if it, oh, nope, I can hear it's right on the edge. Let's knock that back to 12. It's still not super stiff, but it's better than the stock. Let's run it like that, do some testing, and see what we come up with. And just to make sure these things stay, I'm going to click download, which in their parlance means to take the values that I see here on the screen and to download them into the driver and make them permanent. Okay. Are you sure to exit? I'm sure to exit. Okay, let's run the torque testing. This is about as stiff as we're going to get it practically, so let's just go with that. So as always, I'm going to start with the holding torque. And again, you can check out the previous video if you want to understand the testing methodology here. So then I will just pull until it gives up, and we'll measure the peak force. Now you can see it's allowing it to slip, but it hasn't given up yet. And there's our peak is 35.1 newtons. Okay, that works out to a torque of 1.4 Newton meters. Let's start out at 10 RPM. Looks like we got about 38 newtons at 10 RPM. Okay, looks like that is not going to work with that higher gain, so let me dial it back down. Okay, that was set at 12. I guess we're going to have to go back to 11. And now we're going to test at 200 RPM. And I know we didn't test this on the other motors, but I'm contemplating running this through an additional 2-to-1 gear reduction because of its higher speed capability. So we're going to go ahead and test some other numbers so that we can make that comparison. I'm just going to test this to make sure we're really getting 3,000. Yeah, there we go, 3,000 RPM. So that's pretty impressive. You look at the torque numbers, they go straight across, 1.5, 1.5. So there is one other thing I wanted to try. This motor supposedly has a peak torque and a continuous torque, and the continuous torque is, I think, rated around 0.6, and you're supposed to be able to get 2 to 3 times that, which is kind of exactly what we're seeing here flat across the range. So this must be the peak torque, and I believe, if I remember the email correctly, that's for like 10 seconds. So let's see if we can hit a number that's over 0.6 but under 1.5. Like, let's try to target, say, 1 Newton meter and just hold that for a little bit and see how long that takes for the motor to cut out. So let's try 1,000 RPM. And so what are we targeting? Probably targeting something like, 25. So I will try to hold it at about 25 newtons. I will turn off the peak here, and we'll go to 1,000 RPM, and I'll try to hold it right around 25 newtons and see if it runs for a while or if it eventually cuts out. Okay, that's 1,000 RPM. Let's see if I can get up around 25 and just hold it here. And what we've proven is I'm terrible at that, but let's try this again and see if I can hold it better at the desired 25. I'll try just bracing it down here on the vice jaw. There we go. I'll just hold it there. Okay, that was what, 25 seconds, 30 seconds, something like that. I'll have to check the video and see how long that was. But that was impressive. So that was running up in its peak range above its rated torque for an extended period of time, and the pulley is hot. I mean, this is hot to the touch. How hot is that? About 96, so about 100 degrees Fahrenheit. little more here on the side, 104. So the motor's definitely gotten warm. In fact, it's continuing to get warmer as the heat that was generated in the coils is starting to soak out. And no, we're not measuring this or comparing it to any of the other motors, but I thought the numbers were interesting. Okay, let's take a look at the results here and see if we can make any sense of this. And I'm sorry I kind of messed this up by adding some other rows to this, and the reason for that will become evident here in a minute. So looking at this across all of the RPMs we tested from 10 up to 3000, we're sitting right at 1.5, 1.6, 1.4 Newton meters of torque. That's really flat and really consistent, and I'm actually really impressed with that. With the Clearpath, there was a similar kind of a result, but the difference between the peak and the constant torque was really hard. I got some comments about looking like I was pulling the cord faster in some cases and slower in others, and some of that was just due to the way the video was edited. But some of that is because I had to act pretty quickly if I was going to get the peak torque from the Clearpath motor. And this stepper-on line servo seems to have a much wider range of time, which will allow the peak torque output. It's not as high, but it's much more consistent. And I found that kind of interesting. Let's go ahead and put that up here on the chart and look at what we're dealing with. So what we've got here is the bottom blue line. Again, this is broken because I added that 200 RPM data point into the table. This bottom blue line is the 2 Newton meter motor that I've been running on my lathe. And then these two lines, the light gray and the light blue, are the 3 Newton meter motors I tested. One from Automation Technologies and one just from Amazon, the wrap motor, Chinese direct import through Amazon. And so those are the torque curves. And then the top one up here is the Clearpath. And if we come in here, we can turn on the curve for the motor that we just tested. And you can see it's really flat and comes down through here and cuts straight across. So at low RPMs, every other motor actually has more torque. The Clearpath has a lot more, but these 3 Newton meter motors definitely have more. But it's right up here very close to what I've been running on the 2 Newton meter motor that I have had on the lathe for the last year. And so that's interesting. And then as the RPM goes up, of course, it outperforms ultimately all of the motors. So that's interesting. But what's even more interesting is that this motor has the capability to go much higher. It can go all the way up to 3000 RPM. So I could gear it down another 2 to 1. I already have it 3 to 1 on my lathe. I could do another 2 to 1 for a total 6 to 1 reduction, and that would double the effective torque. And I can do that because this retains its torque all the way up to 3000 RPM, as we saw in testing. So I'll create, let's imagine doing this with the 2 to 1, and I'll create another column out here. So let's get the RPM. So it'd be equal to this value divided by 2, because gearing it down will cut the RPM in half. So we'll put another column out here for the RPM values, so up to 1500 RPM instead of 3000. And then let's create another value out here, which is the torque times 2, because the torque will be multiplied by 2. And then let's create another data series for this. And turn that on. And that gives us this sort of dirty brown line that comes across here. So this is what we should expect if we run that through a 2 to 1 gear reduction. You can see it's double the torque. And the reason we can do this again is because we can extend that motor all the way out to 3000 RPM. The Clearpath motor can't do that. The maximum RPM on it is only 1800. And you can't do that necessarily with these other motors because the closed loop steppers, once you get up to 3000 RPM, they've got just nothing. I didn't even test them up there because if you try to run them that fast, the drives tend to panic. But if you look at this, what this means is with that additional 2 to 1, this becomes very, very interesting. It outperforms certainly the 2 Newton meter motor I've been using. It outperforms both of the 3 Newton meter motors that I tested. and it gives the Clearpath a run for its money, which makes sense because it's 180 watts and the Clearpath is only about 200. So they're roughly in the same class. So I think this is really interesting, and this is something that we should test. Let's go out and put it on the lathe, rig it with another 2-to-1 gear reduction, and see how it performs in practice. Okay, I have this motor installed on my lathe. I'm using the same temporary bracket on the front. I'll put it in the back at some point. I've got it wired up. Of course, there's no place for the enable line to go, so I've got that clear and out of the way. This is hooked up with the belt drive that I was using with the other motor, which is 3-to-1. Now we actually want to run this with 6-to-1. And I fortunately have a gearbox here, and I can add another 2-to-1 gear reduction. So I can see I'm on 1A, which I know is straight through on the gearbox. So I can see that 1A, on the feed it would be 6 thou. If I set it to 1C, it would feed 3 thou, which means that adds another 2-to-1 gear reduction. So I'll set it to 1C. And so now I've got 3-to-1 reduction here plus 2-to-1 through the gearbox, so I should have 6-to-1 overall. I originally had this set up to run 1,000 pulses per motor revolution with the previous motor I have on here, and I have this motor set instead to 500 pulses per revolution. So in total, the motor will run twice as fast, and I've got another 2-to-1 gear reduction, so I should still be set up, and everything on here should be correct, and we should be able to make some test cuts. Power this up, and yeah, the motor's grabbed. So initially this comes up with 5 thou per revolution, and I can turn this, and you can see the pulley down here turning, and I can see the screw turning, so it's going the right direction. So let's go ahead and just make some cuts. What I have in here is a hunk of 1018. This actually is the remnants after I used a rotobroach to hollow out years ago when I made the tool post grinder. So let's just start by turning this down and using the feeds and see how it goes. Okay, that was about 20 thou, total depth of cut 10 thou per side. Let's go ahead and push it to 30 and see what happens. That's going great. Push that to 40. Looks good. 50, which is 25 per side. No problem. Let's go ahead and bump up to 7 thou per rev. Eight. Yeah, it's having no trouble with that at all. And I'm getting nice golden chips off of here that are breaking easily. Part's getting hot. Let's see where we are. I want to go ahead and thread this, and I've got a nut here that is 5/8 11, so let's just shoot for that. So I want to shoot for about 615, and it looks like I'm at about 782, so I've got a little ways to go. Okay, 616, 617. That is about what I need. That is real hot. But let's prepare for some threading. Let that cool for a minute. And I do want to just play with the feed here a little bit and just sort of get a feel of trying to stop it with the feed handle here. So the feed handle here has a tremendous amount of torque that it can apply. So that's actually relatively difficult to stop. In fact, that's way better. I mean, I can stop it, but the motor immediately recovers. And just my impression of doing that by hand is that that is way better than with the closed loop stepper that I was using. When I was using that, it died almost immediately when you tried to grab this thing. So this is a ton more practical torque. Now, I don't know how the numbers, we can look at it. I don't think it actually comes out to a lot more torque than what I was measuring on those motors. But in a practical sense, I like the way that feels. Now, I can stop it without it panicking and then it catches up. So let's see what happens when we actually try to thread. So I'm going to switch this over to threading, and I'm going to set it up for 11 threads per inch, which is what my nut here is. Does this look plausible? Yes, it does. And let's start by chamfering the end, and I'll just use the threading tool to do that. Okay, and let's just give it, say, 3 thou, and we'll go ahead and make a pass here. That looks like 11 TPI to me. Okay, let's just make some passes, and I'll go ahead and put a little oil on here. Cratex stick. I'll go ahead and blend this up a little here. Well, that thread is nice and clean. There's not really much rock in it. There might be 1 thou of play, which is about, what I would want. It's not a machinist fit, but it's a good practical fit on that thread. And more importantly, there's no difference in the feel of the thread right out on the end versus back in the middle, which means that even with coming into the heavy thread and putting strain on the servo motor, it maintained its position very well and didn't distort that thread. And we had a lot of heavy engagements. There were a lot of places where I jammed it down and there was a big lurch on the carriage, and I was sure we were gonna pop the motor or have it give up, but it didn't. It held in there. So I am actually pretty impressed with this thing. I really, after I first powered it up and saw the softness of it, I really expected it to not do a very good job of maintaining position in a positioning critical application like this. When I ran into all the issues with their tech support and their documentation and their software, I expected this thing to just be a lost cause, but honestly, for 99 bucks, it works pretty well if you can use the default settings. So for this setup on this lathe, I think I'm gonna leave it on here, probably make a mount and get it in the back finally. But I'm pretty happy. I think I'm gonna live with this for a while and see how it goes. And so far it looks really good. I think I would recommend this motor for the electronic lead screw on a 10 by 20 size lathe like this. The other motor that I would also recommend would be that rat motor that we tested last time, which is a closed loop stepper. The difference in that is it's going to have more torque. You only need to run it 3-to-1 reduction on this size lathe, and but it's going to make more noise because it is a stepper motor, and so you are going to hear the kind of whine of it when it's running all the time, which irritates some people. Doesn't bother me that much, but I do like how quiet this thing is. So I will put links to both of those motors down in the video description. Be aware those are affiliate links. If you use those and buy something, it helps to support me in the channel here. Doesn't cost you anything, but if you're not into that, it's fine. I've given you enough information. You should be able to go look these up on your own and avoid that if you don't want to. Well, that's all I've got for you today. If you enjoyed this video, please give it a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Tell me everything I did wrong with my testing setup. I know you were you're probably already down there doing that anyway. And if you've got other ideas for how to do it better, by all means, get some motors, do some tests, put the stuff out there for the community so that we'll all have better information. Thank you for watching.